SwayamPrabha. Digital India. Educated India.
Welcome back. This will be the last part of the topic on Exergy. We were discussing the Exergy balance for the for fixed mass or closed system. Okay, and we've done some certain exercises. We will continue our discussion, particularly now for control volume. So this is a representation of the control volume, and what we have done is we have illustrated this in terms of sign as well, that there is a heat supplied in and the work done on the surrounding, and thus the corresponding exergy would be X heat, which will be your net exergy in, and this will be your net exergy out. Okay, so we can write down the balance. So in addition to the work and heat exergies, we will have to now include the exergy due to the mass in and out. Okay, so this would be your net exergy in, and we can minus your next exergy out. What we are doing is we are trying to keep the same nomenclature as we have used for energies or simple energy balances. So this is your heat in, work out, exergies, and now I'm going to write here your mass in minus mass out. Okay, so in other words, this is nothing but your exergy transfer to the system, this whole term, and then I'm going to subtract minus X destroyed. Okay, and this would be your change in the exergy of the control volume. Okay, now you can write this in terms of your summation 1 minus T0 Tk. Okay, this will be your X heat, and this is going to be your W minus P0, V2 minus V1. Okay, and what about the X mass in and mass out? So this we can write in terms of your summation m xi. Okay, so this will be your in and this will be your out. Okay, so we can write this in terms of rate form also. Okay, so this would be your 1 minus T0 Tk Qk dot minus W dot minus P0 dVCV dt plus summation m dot psi in minus summation m dot psi out minus X dot destroyed is equal to dxCV by dt. Okay, so this is the rate form for the exergy balance for control volume or open system. In case your initial and final state of the control volume is specified, that means you know your x2 minus x1, then you can write this in terms of your m2 phi 2 minus m1 phi 1. Okay, so note that this phi is exergy of the non-flowing system. Okay, that is corresponding to your control volume. So this is when your initial and final state of the CV is specified. Okay, are specified. So now what we can do is we can look at exergy balance for the steady flow devices or steady flow systems, and we know that most of the devices which we are interested in, such as turbine, compressor, pump and so forth, operate at steady state conditions. Okay, so for such case what we can do is we can consider the change in the properties to be 0, that means your dxCV to be 0, and we can write this rate expression in this form. Okay, so this is due to heat, work, mass, and then you have to also include the destroyed. Okay, so let me first look at the single stream here. So when there is only one stream is involved, which would be most of the cases for turbine, compressors, nozzle, or when we consider only a single stream, then you can write this mass term in this form. Okay, and then this expression can be simplified. Now x1 and x2 can be related to your, or we can write x1 minus x2 in this form which we have derived earlier. That is a definition of flow exergies. Okay, now it will be a change in the exergies of the flowing fluid. So for the unit mass expression, the same expression can be written in this form. So this is much simpler form now. Okay, so this is the Exergy balance for the steady flow system, and so now we can make use of and this is a representation in some form. Okay, so before making use of this expression to solve the problem, so let us first look at reversible work. Now Exergy balance relation presented in the previous slide can be used to find out the reversible work by setting the Exergy destroyed equal to 0. So when you say x destroyed equal to 0, then the corresponding work is going to be W reversible. So you can plug this information in the previous expression for the Exergy balance for the control volume. And then it turned out to be that your W reversible is simply equal to the change in Exergy due to the flowing fluid plus the heat transfer contribution, okay, or the Exergy contribution due to heat transfer. For the case of adiabatic system, this is going to be simply m dot times your psi 1 minus psi 2. So what we stated here is that for the case of a reversible system, your W is simply a W reversible work, or in other words, x destroyed is 0. That means x destroyed is 0 for reversible work, and this particular work, okay, represents the maximum work output for work producing device such as turbine, and the minimum work input for work consuming device such as compressor. Okay, so this we have emphasized many times in this particular course. Now these aspects of reversible work. So now let us look at the efficiency of steady flow devices. How do we make use of Exergy to evaluate the second law of efficiency? Now, so we already mentioned the second law of efficiency is nothing but your ratio of efficiency with respect to your corresponding reversible devices, or such as devices based on the Carnot cycle, and this can be written in terms of Exergy recovered, Exergy and Exergy supplied. So this is the definition of second law of efficiency. So what we are going to do is we will just take the ratio of Exergy recovered and Exergy supplied. Now let's take an example for the turbine. Okay, if we consider the kinetic energy, potential energy negligible, and the device is adiabatic, then what would be the energy recovered for turbine? Is going to be simply the net work out from the turbine. And what would be the corresponding Exergy supplied? That will be your simply your psi 1 minus psi 2, the fluid which is being used, such as steam, in order to for the network. Okay, so the Exergy recovered is W out, and as Exergy supplied would be simply psi 1 minus psi 2 for the case of adiabatic turbine, where we have considered kinetic energy, potential energy are negligible. Okay, and this can be now also written in terms of H1 minus S2. Okay, this would be clearly a H1 minus S2 for isentropic process, which we have already looked at when we discussed the entropy part. This term is nothing but your W reversible out. Okay, so this was exactly the case where we consider the efficiency with respect to Carnot cycles, okay, or reversible cycle. So now let us take other examples. Okay, before I do that, let me also touch upon this fact that this second law efficiency based on Exergy can also be rewritten in terms of this term, where you can write this, okay, in terms of 1 minus T0 x generation, okay, which is nothing but x destroyed. So this could be simply written as 1 minus Exergy destroyed divided by Exergy supplied. Okay, clearly Exergy recovered is nothing but Exergy supplied minus Exergy destroyed, and thus since Exergy destroyed is T0s generation, thus you can write your efficiency in this term. Okay, so S generation is nothing but your S2 minus S1 for the case of adiabatic system which we have considered. Okay, now we can extend this for adiabatic compressor. Adiabatic compressor, the efficiency would going to be Exergy recovered again divided by Exergy supplied. What is Exergy supplied? It is the work done or work in to the compressor, and Exergy recovered is simply the change in the flow energy, okay, of the fluid, which will be your psi 2 minus psi 1, okay, and this also can be written in this form. So you can also write this efficiency of the compressor, second law of efficiency of the compressor, in this form, in the form of generation. So now let us look at for the second law efficiency for heat exchanger. Okay, now here is a heat exchanger with two unmixed fluid stream, and in order to find out what is the exergy expended, so what we can consider here is the hot stream is 1 and 2, or particularly 1, which loses energy to cold stream, and thus your exergy expended is a decrease in the energy of the hot stream. What about the exergy recovered? So this is nothing but exergy supplied. What about the exergy recovered? Is the increase in the exergy of the cold stream. So this would be exergy recovered is going to be the exergy increase in the cold stream, and thus we can find out the ratio of the recovered. This is your exergy recovered, and this is the exergy supplied or expended, and thus this would be your second law efficiency of heat exchanger. This you can also write in terms of generation, and based on the steady state condition you can find out the X generation in terms of changes in the entropy of individual streams. For the case of a mixing chamber, that means your 1 and 2 gets mixed and forms a mixture of 3, the exergy supplied is going to be 1 minus 3, that would be exergy supplied, and exergy recovered would be corresponding to your 3 minus 2, changes in the flow energy, flow exergy of 3 minus 2, okay. So that will be the ratio for the case of mixing chamber, okay, and that will be your second law of efficiency. So one has to do this analysis very carefully to make sure that you find out the exergy recovered correctly and exergy supplied correctly in order to find the second law efficiency of such devices, which we are going to say steady flow devices, okay. So we can end this lecture with this example. The first example is exergy analysis of steam turbine, which is we are going to consider steady flow device, and this is your control volume, okay. What we need to find out is the second law efficiency of such a steam turbine, and then the second thing which we have to find is basically the exergy destroyed. So you can go start with the exergy balance here. What we have to calculate here is the maximum power output or the reversible power, which is determined from the rate form of exergy balance, okay, which is applied to the extended system. So we are going to consider steam system plus surrounding, okay, and in that case your X destroyed is going to be 0 considering the reversible, and you can write down this expression in this form considering steady state device. So you have this mx1 plus is equal to W reversible out and plus X heat. Now considering that we have taken system plus immediate surrounding, so here we have considered system plus immediate surrounding. So the boundary of the immediate surrounding is at environment temperature T0, or considering this extended system, your X dot heat is going to be 0, okay, and thus your W reversible out is nothing will be simply this expression, and you can find out the reversible. Now this would be the condition for your reversible maximum power work based on this exergy analysis of extended system, where you consider system plus immediate surrounding. The reason for immediate surrounding you consider because that would be the yield the maximum work for such a system, and then we can find out the effective X destroyed, okay, based on the total X destroyed would be simply this, where this would be the for actual out and this will be your reversible out, okay, which we have calculated from here, okay. So this would be the destroyed exergy, and of course you can calculate the second law efficiency by taking the ratio of W out and reversible out, okay. So we can extend this exercise for exergy balance of a charging system. So here again, so you have this particular tank containing air, and which you are using compressor to fill the air, so it's a charging process. You can consider this extended system here as well. So our interest here is to find out the minimum work required for the process, okay. Now in order to find the minimal work, what we have done is we have also considered here this reversible process. So x destroyed is going to be 0, and x in minus x out is basically x2 minus x1. Your x1 and phi is 0 because initially air in the tank and the air entering are at the same state of environment, and hence your psi 1 and phi 1 equal to is basically 0. Okay. So this is going to be your minimum work required for a process which is reversible. Okay. Note that I have not included any heat transfer, because what we have done is we have considered also here extended system plus your immediate surrounding, such that your boundary of the immediate surrounding is at the environment temperature T0, and thus your exergy transfer is due to heat is 0. Okay. And by considering that, we have got in this case a minimum reversible work for this particular process. Okay. So this is the exercise which we go to perform, making use of exergy in order to find the maximum or minimum work, and of course making use of other assumptions. If it is air, we are going to make use of ideal gas, and thus we can calculate your minimum or maximum work, and doing so we can also evaluate second law efficiency based on exergy information. Okay, so this would be the end of the particular topic. So let me just summarize what we have gone through in this particular topic on exergy. We defined exergy, which is nothing but availability, available energy, or useful work, or work potential of energy. Okay, and we also looked at reversible work, irreversibility, second law efficiency we talked about. We made use of exergy in this. Okay, we defined exergy change of a system for non-flow and flow system. Exergy transfer occur by heat, work, and mass. And then we define that decrease of exergy principle is also equivalent of your second law of thermodynamics, and we also define the exergy destruction, which is your related to entropy generation. And then we looked into the balances for the closed and controlled volume, followed by few very short examples illustrating how to solve such problems. Okay, so that will be the end of this topic. So hopefully this clarifies the making use of second law in more clear terms called exergy, and we'll start a new topic.